Hey, my dear NEET warriors, welcome, welcome, welcome. Hello, Aka, Hudaya, Mishra, Subhashni. Welcome, Viranjana. Hello, Only Study. Good evening, my dear warriors. And you're watching the you're watching the NEET Conquer series. And this is the first lecture of rotation. I have divided the chapter of rotation and rigid body into two parts, part 1 and part 2. In this part 1, we will be seeing concepts of moment of inertia, the parallel perpendicular axis theorem, and how to find moment of inertia in general. Then we will talk about how to find torque and how to use torque is equal to I into alpha equation, and pulley problems with mass, toppling problems, equilibrium problems, all these things in this lecture. In lecture number 2, I will be dealing with angular momentum, conservation and rotational energy. So this is how I have divided both these parts because they need their own space and time. So we will keep them on separate days. I know you guys were all eagerly waiting for this lecture for a long time, and here we are after a week. Nice to see all of you. Hello Senthil Kumar, Subhashni, hello Vedanjini, hello. Good evening Jyoti Kumar, good evening. And thank you for smashing the like button. It means a lot. I keep seeing your comments after the session and it shows your enthusiasm. It shows what you want next. So keep the comments flowing, not just in the chats, but also if you're watching it recorded or even live after the session is over, make sure you write the comment on how you enjoy the class, what you want next, how are your studies going, and the awesome community that we have of all the NEET students. They help each other out, they solve each other's doubts, and that's the best part about this particular channel. And those of you who missed joining the Avenger batch, make sure you take the entry into the Avenger batch. Entries are still open. You make sure you check out the link which is there in the description box below and join the Avenger batch, which is the one-fledged solution with my lectures in English and all the chemistry biology classes also available. And you have to use the coupon code CAPTAIN for any course, be it Avenger, be it the test series, be it the subscription. The code is CAPTAIN, CAPTAIN. You will get the maximum benefit that you can possibly get on any of the courses. And I have a very important surprise for all of you and very important notice, and that's about the special free classes which I'm going to conduct for all of you in the days to come from 4th to, in fact, not just 6th, 7th of November. So these 3-4 days I will be conducting free special classes for you, on demand classes. So the first class is going to be on top PYQs of mechanics. All the amazing chapters, be it from vectors, kinematics, rotation, collision, center of mass, work energy, circular motion, Newton's laws, friction. All these chapters combined, top mechanics PYQs one session. Then modern physics, be it semiconductors, nucleus, your atomic structure, photons, photoelectric effect, wave particle duality. All these chapters combined, modern physics, very heavy weightage unit, a special class on that too. And then another special class for logic gates, my dear warriors. So a special class for logic gates also coming in for all the students who are preparing, right? So please mind it that these classes won't happen on YouTube. This will happen on the platform. It's absolutely free of cost on the platform. There will be a link which I'll be sharing very soon. Stay tuned in this space because this is a festival for all of you in this upcoming Diwali. All right. So I want to see all of you over here. Good evening. Nice to see all of you over here. And I'm pretty sure you will all be excited and mark your full attendance in these classes, okay? Because this is not going to be repeated in any form, in any way, anywhere else. Cool? So let's begin with our lecture. Let's start with this concept of inertia and moment of inertia. See, if there is a Pandu and this Pandu is asked to push a rock over here, he will find it difficult. He will find it difficult to start its motion. Maybe it was at rest initially, right? Maybe it was at rest initially, and then slowly it gains some velocity, maybe 2 meters per second, and then maybe after some time, maybe it gets 5 meters per second. So definitely there is some resistance to change the state of translation. And this resistance to change the state of translation is basically your mass, which is also called as just inertia, right? And we know mass is basically expressed in kg, that is the unit of mass, and you measure inertia with mass. How difficult it is to start the motion, how difficult it is to stop something, how difficult it is to change the state of translation. That is inertia. Now imagine Pandu went to a park and he saw that there is a champa on the merry-go-round. Very, very beautiful champa it is, and she's on the merry-go-round. So Champa asks Pandu, please give me a push. Rotate me on the merry-go-round. So Pandu goes over there. And he gives a nice push to that merry-go-round. So the merry-go-round begins to rotate. So now there will be some resistance encountered. Depending on where Champa is standing. What is the mass of Champa? Where is there? She's thin Champa or fat Champa? What is the axis of rotation? How is that axis? Where is it placed? All these things are going to matter. So there will be a resistance, I would say. There will be a resistance, right, to the change of the rotational state, Maybe it was at rest initially, maybe it now starts rotating at 2 rpm rounds per minute, then maybe after some time it starts rotating at 6 rpm. So you are changing the state of rotation, you are changing the speed, so you are changing the state of rotation. This resistance to the change of state of rotation is called as not just inertia, it is the rotational inertia, which is called as moment of inertia, or sometimes also called as rotational inertia. The symbol for that is capital I. It is just like mass, but for rotation. You have a fan, you want to rotate it. How difficult it is to rotate the fan. You are holding a stick, you want to rotate it. How difficult it is to change the state of rotation. I have a wheel, I want to spin it. How difficult it is to spin it. That resistance is measured by rotational inertia or moment of inertia given by the symbol I, just like you had mass for translation inertia. Is that understood? Thank you for all the love from Manipur. I would say in the Telegram link, instead of t.me, just put telegram.me, the link should work. Okay, replace that alphabet T with Telegram, it will work. Cool? Everyone with me on this? Great. Now, what does this moment of inertia, depend on? What does this moment of inertia I depend on? It depends on mainly three things for a particular body. So if you have some random body, and let us just say this is the axis of rotation. This is the axis about which the body rotates. The moment of inertia depends on three things. Number one, the mass of the body. It depends on the mass of the body. Number two, it depends on which axis are you rotating. Like this, like this, like this, like this. How are you rotating it? Are you rotating the same body like this, like that, like this? So depends on the axis of rotation. Depends on the axis of rotation. And there is one last thing. Maybe the axis is the same. Maybe it is the vertical axis. Maybe the mass is the same. But let's say the masses are far away from the axis. Maybe in some other body the masses are close from the axis. Like in the example of Champa rotating on the merry-go-round. Imagine the same Champa comes close to the axis, I think it will be easier for Pandu to rotate, because Champa, when she comes close to the axis, she will go in small circle. So it will be easy. But if Champa is on the end of the merry-go-round, she has to go in a big circle. She has to go in a big circle. So I think the effort will be more, resistance will be more. Do you guys agree with this statement? Do you guys agree with this statement? Hence, I would say the resistance also depends on how far the masses are from the axis. That is basically called as the distribution of the masses. That is basically called as the distribution of the masses. These are the three things on which the moment of inertia of a body depends. Is that clear? Everybody with me on this? Cool. Give me a thumbs up. Okay, mass of the body. How are you rotating it? That means axis. And how far these masses are from the axis of rotation. So what is the formula for finding the moment of inertia? I would say there are two formulas depending on what kind of body it is. One is basically your discrete system. Okay. The other one is basically your continuous body. What is the difference between the two? In discrete system, if you probably have this as the axis, okay, if this is called as the axis about which it is rotating, here also, let's say, this is the axis, okay, this is the axis about which the body is rotating. In case of discrete system, you will see particles are separate. You can count them. They are point masses placed from the axis. Like imagine there is a molecule and that molecule is rotating. So they are like point masses which are rotating about an axis. Or you take small tiny steel balls and these steel balls are revolving around an axis. That is also a discrete particle system or discrete system. Each of their masses might be m1, m2, so on and so forth till mn. Each of the particles might be at a different distance from the axis. So let's say this is R1, let's say this is R2, R3, like that, Rn. Correct? Then the moment of inertia formula is simply m1 R1 square plus m2 R2 square, like that till mn into Rn square. So essentially moment of inertia is summation of all the masses and the distance square from the axis from 1 to the nth particle. From 1 to the nth particle. So this becomes your formula, my dear students, for finding the moment of inertia for particle mass system or discrete mass system. For a discrete mass system. Very good. But what is the meaning of continuous? Like a ring, like a disc, like a sphere, like a cylinder, like a cone. How many particles are there on a cone? Infinite. How many particles are there on a sphere? Infinite, countless. It's continuous, smooth transition. You can't count the particles. So that is basically your continuous body. In such a case, what you do is you take a small particle element, which is a dm, and that element will be at some distance from the axis. Let's say you call it r. R will be different for each and every particle. This is an elemental mass. This is an elemental mass. This is an elemental mass. The moment of inertia of that element will be di. That will be nothing but dm into r square. Therefore, the total moment of inertia will be the sum of all the small moment of inertias of all the elements on the body. The sum means integration. Integration means accumulating, adding all the effects. So I am adding all the small moment of inertias of all the dm masses throughout the body. So my dear warriors, the moment of inertia will become integral dm r square. That is the formula for continuous body systems. For basically continuous body systems. This is for discrete mass systems. We will be taking up problems for both so that you get an idea about it. Everybody, right? So let's begin with some basic problem solving. Then we'll go to some more complex questions. So let's say, for example, there is a system, okay? Example, there is a system, and I will show you the axis over here, all right? And what you have is there is a 3 kg mass at a distance of 2 meters, and at a distance of 1 meter, you have a 2 kg mass, like this. In this situation, at a distance of 2 meters, you have here a 3 kg mass, and over here at the same side, here you have the 2 kg mass. In both the cases, this is the axis of rotation. Here, this is also the axis of rotation. Question is, compare the moment of inertia, who is more, who is less, and find the values also in each case. Compare and find the moment of inertia for both the situations. One might generally think that the mass present on the same side or on the opposite side might actually change the value of the moment of inertia. But if you observe this formula carefully, you will realize the sign of R does not matter. Whether R is on this side or on that side, positive, negative, doesn't matter, because you are squaring it. You square a negative number, it just becomes positive. So really doesn't matter, guys. And at the end of the day, R is not positive or negative. Keep that also in mind. Actually, R is the distance, and distance is always positive. It's the distance from the axis. So if I had to write down the moment of inertia, in the first case, it will be the mass 3 kg into distance, which is 2 square, plus mass into distance, which is 1 square. That's it. So 2 square is 4. 4 3s are 12. 1 square 1. 1 into 2 2. So this is going to be 14. What might be the unit? See this, kg meter square, kg meter square, kg meter square, everywhere. So this will be kg meter square. How many of you got 14? Very good, Priyanka. Very good, Senthil Kumar. Amazing. Here also there is no difference. It's the same thing. What difference does it make? So the moment of inertia in this case also mass into 2 square plus mass into 1 square. So you are still going to get this as 14 kg meter square. It really doesn't matter. Not just that, just imagine, instead of showing the axis like this, I would have shown the axis rotating this way. Still the moment of inertia is going to be 14 only. Whether you rotate clockwise or anti-clockwise, doesn't matter. Just like whether you push a mass this way or whether you push a mass this way, doesn't matter. The mass is the same. Same way whether you rotate like this or like this, moment of inertia will be the same. Keep that in mind. Everybody with me? Right? Similarly, imagine, I tell you, listen, there is a ring. Somebody is rotating this ring. This ring which is there, it has a radius of r and it has a mass totally of m. I want to find, if this is the axis of rotation, what is the moment of inertia? What I will do, I will realize first that this ring is not one particle or two or three. There are infinitely many particles. It's a continuous body. So I cannot use this formula. I have to use this formula. It's a continuous body. Correct? So what I will do, my dear students, I will divide the ring. Okay, that ring which is there. This is the axis, right? I will divide the ring into small elements. Each element is a dm mass and each dm element is at a distance, small r. But the best part, this small r is going to be same for all the particles. It's going to be same for all the particles and it will be equal to r. Oh, perfect. So when I write the formula of moment of inertia, which is integral, r square dm, I might as well write it as a capital R square dm. But wait a minute, r is a constant, so I can bring it outside the integration. So it will be integration of dm. Outside you will have r square. Now you will be wondering, sir, what is the integration of dm? Integration of dm means adding all the masses on the ring. dm plus dm plus dm plus dm plus dm on the ring. Adding all the masses on the ring, I will get the total mass of the ring. Understood? I'll just get the total mass of the ring. So it will be r square into m. Usually you put m first, r second. So mr square is the moment of inertia of the ring. So this is the moment of inertia of the ring. Is that very, very clear? Understood? Clear? How we used the continuous body integral formula. Now imagine if it was a disk. If it was a disk means it's like multiple rings. Yes or no? If it's a disk is nothing but made up of multiple small elemental rings. A disk is a combination of multiple rings from smallest radius to increase till the circumference, right? The periphery. Oh, so then what will I do for the moment of inertia of the disk? The moment of inertia of the disk is take the moment of inertia of the ring as a di. You integrate it from 0 to r. You integrate it from 0 to r. And when you do the integration, the answer which comes out for the disk comes out to be m into r square by 2. This is the formula of moment of inertia for a disk. This is the formula for moment of inertia for a disk, my dear warriors. Everybody with me? Yep. Awesome. Keep this in mind. Similarly, one can also take a rod. One can also take a rod like this. And this rod has a mass of m, and this is length L. This is basically your length L. And this is the central axis about which you are rotating the rod. Central axis about which you are rotating the rod. Again, do the same technique. This is a continuous body made up of infinitely many masses. You take any dm mass, and assume the distance from the axis is x. So the moment of inertia di will be nothing but dm into x square for that element. So now what you should do is basically to find the moment of inertia of the rod, you add all the small moment of inertias, from all these elements here to here, dm, everywhere you add it, you will get the total moment of inertia of the rod, right? This will come out to be as ml square by 12. This will come as ml square by 12. This is something which you should again remember. Please note that derivations will not be asked and are not important for NEET perspective. Even if you do not know the exact derivation, it's okay, but you should have an idea of how it might come, or basically you are using that integration formula. Is that okay? So this is how you can find the moment of inertia of different bodies, how resistant they are to rotate, how difficult it is to rotate these bodies. We can find that out. Similarly, you can find it out for a hollow sphere. Other word for that is basically a shell, spherical shell. And the second one, guys, hopefully I have I don't have a 3D diagram, no problem. Okay, this is basically your, this is your solid sphere. Both of them are going to be rotated about their central axis. In case of in case of a solid sphere, the moment of inertia for a solid sphere comes out 2 by 5 times mr square. 2 by 5 times of mr square after integration, whereas the moment of inertia of a spherical shell comes out as 2 by 3 times of mr square. This is the answer, guys. This is the answer. 2 by 3 times of mr square. Is everybody clear till this point? Remember all these values. Remember all these values now. For a ring, starting off with a ring. For a ring, it is mr square. For a disk, it is mr square by 2. For a rod at the center, ml square by 12. For a solid sphere, 2 by 5 mr square. For a shell, 2 by 3 mr square. So let's say we do a question. Very interesting question. Imagine there is a disk. Okay. It is made of, let's say, iron. Okay. And it is rotated about the central axis. And the moment of inertia that comes out is basically I. How much does the moment of inertia come out? It comes out as I. Now you take a much larger iron disc. A much larger iron disc. In fact, the radius is doubled. The radius is basically doubled. About the same central axis, there will be some new moment of inertia. I will call it I1. I1 is how many times of I? That is the question. Old moment of inertia was I. New moment of inertia is I1. How many times more it is if the radius is doubled? This is also made of iron only. If you give me the answer correctly, you are guaranteed top 500 rank. Guys, in the NEET exam. Who are the top all India rank 500 NEET 2024-2025? I want to know right now. In the chats. And guys, if you have forgotten to smash the like button as of now, make sure you do that. And if you have forgotten to subscribe, do that right now. Or else you're going to miss all the awesome classes which are going to be conducted right over by your own Captain Shreyas, your physics educator. Cool. Alright. So many of you are claiming, sir, we are going to get top 500. Let's find out. Okay. So let's find out. Don't worry. Even if your answer is wrong, you are going to learn from the mistake. And because you realize the mistake, you are going to get 500 either ways. Don't worry, guys. So, moment of inertia of a disk. Formula is mr square by 2. That is the formula for I. Now think what will happen in this situation. In this particular situation, I1 will be mr, but r won't be r. R will be basically 2r whole square by 2. So a lot of people think that it is 2 square. So it is 2 square. That means it will be 4r square by 2, right? And this will be that mr square by 2 over here. So it will become 4 times. That's what most of you thought. But there is a common mistake. Who said the mass is going to be the same? That is the mistake which many students do. The mass may not be the same. It is some other mass only. Why? When you increase the radius, that more radius will have more mass. No. Think logically. This much radius had this much mass. This much radius will have more mass. How will the mass be the same? So many people forget that mass. Now, how will the mass be calculated? Simple. Mass is proportional to the area. Bigger area, bigger mass. More area, more mass will be there. Small area, small mass. It's a disk. It's a two-dimensional object. So I can just say over here, so for a two-dimensional object like a disk, the mass is directly proportional to the area. and area is directly proportional to the radius square. So think about it, what will happen? Think about it, what will happen? The new radius is 2 times the old radius. So r1 square will be 2r whole square, which is basically 4 times of the r square. So the new mass will be how many times the older mass? It will be 4 times the older mass. Is that clear? Is that clear, everyone? So mass will be 4 times. So m1 technically is 4m, guys. So 4 4s are 16. So 16 mr square by 2. Mr square by 2 is just I. So 16 times of I. 16 times of I. Answer is 16. If you wrote 16, very good. Understood the mistake? Nice silly mistake, no? Did you love the silly mistake which many students do? They forget that mass. Okay? Which you also might have done. Don't feel bad about it. Because you attended my class, now you will not make the mistake. You will be in the top. You will be in the top. Very good. Keep it up. Moving ahead now to the next question. Now, in this particular question or this set of questions, you will see probably it's not a complete figure, it's a part of the figure. Okay, it's a part of the figure. So look at this. Everybody loves eating pizza. So I take a slice of the pizza, which is like the sector of an arc. And let's say this angle, maybe take it as 60 degree, doesn't matter. The mass of the slice is m, the radius of the slice is r. It's a part of a big disc. The remaining disc has gone, only a small part of mass m is remaining, and this is your axis. Just like before. Question is, find the moment of inertia. Find the moment of inertia of this small slice, pizza slice, which is there. Okay, so there are very crazy things which you can think of, but there are only few things will be correct and it will be appropriate, else you will get a wrong answer. So let's see, what do we do? Let's complete the pizza slice. Let's add, no, because it will make a disc. And disc is a known figure. Sector, I don't know. Full disc, I know. Okay. So if I look at it from the top or even the side view, it's okay. If this was the slice, how many more slices, identical such slices, should I add to make the complete disc? Think about it. Each one is 60. How many times should I add so that I'll get 360? Obviously 6 times, right? So I'll need 6 slices. So won't I need basically 6 slices, guys? Everybody? So I will need basically 6 slices. 6 slices together, right, of the sector. Okay, so this is your axis. Very good. Now, if I ask you, what is the total moment of inertia of the disc? The total moment of inertia of the disc. You'll be like, yeah, it's the mass r square by 2. What is the mass? Oh, be careful, it is not m. Each slice was m. How many times? 6 times. So this will be 6 times m into r square and divide by 2. So 6m is the mass. Lot of students forget that the number 6 should be there. M is the mass of each slice, so 6 slices, so 6m. But this moment of inertia of the disc is also moment of inertia of each slice multiplied by 6 times. So it is 6 times the moment of inertia which you want to find for each sector, I would say, which is equal to 6 times mr square by 2. You know the best part in this problem? This 6 just got cancelled and I just got that the moment of inertia of that sector which I want to find out came out to be just mr square by 2 again. This is amazing. Because it is same like the disk formula. Not just that, even if this was not 60 degree, if it was some other angle, 45 degree or 30 degree or 10 degree, what will happen? Here this number will change, number of slices will change. If instead of 6 this was 8, then this will also be 8. If this is 9, this will also be 9. If this is 5, this will also be 5. So if this is 6, this is 6. If this is 5, this is 5. This is 8, this is 8. This is 9, this is 9. They will cancel no matter what. So doesn't matter how many slices you make, doesn't matter what angle you keep, whether it is 60 or 40 or 30 degree, all right, always the answer for such kind of a question will come to be mr square by 2. Isn't it a fascinating question? Isn't it a fascinating question? So many students thought it would be 11 ml square by 2, 12 and all those things. No guys, it will not be. Each of the slice has some inertia. Each inertia, if you add it totally, you will get the total moment of inertia of the disk, which is nothing but this one, mr square by 2 is the one of the sector. Yep, answer will be the same. Correct. Very nice. Now, what happens is, somebody tells you, listen, there is some two-dimensional object, and the moment of inertia is, example, 3 kg meter square. Just randomly I have taken some value about some axis over here. Now what you do is, you take the same axis, you take the same figure, whatever is there, something like this, right? Okay. But you stretch it. So it looks something like this maybe. Check this out. See if this is okay. Yeah, maybe something like this. You stretch it along the axis. You are basically stretch along the axis. In this scenario, what happens is, if there was a mass here, that mass will be stretched like that. If there was a point mass here, think about it, that mass will be stretched like this. Has the mass changed by elongating it? Same figure from 2 dimension, I made it into 3 dimension. Has the mass changed? Come on, my dear students. Has the mass changed? No, right? Mass has not changed. Everybody agrees that same mass has been stretched. Axis is still the same. So axis also has not changed. Axis also has not changed. Everybody with me? Pakka? Now, next thing. Has the mass distribution changed? Well, if this mass over here, if this particular mass over here was here, I stretch it. It is still at that same distance. Whatever distance it is still at that same distance. It has not changed from the axis, whatever the distance was. So, has the distribution changed? No. In fact, these 3 factors only decide the moment of inertia. So, should the moment of inertia change? Should the moment of inertia change? Think about it. Obviously, no. So, hence, this will also have the same moment of inertia. This is the stretching property of moment of inertia. What is this called? The stretching property of the moment of inertia. So, when you stretch a 2-dimensional body into 3-dimensional body, then the moment of inertia will not change. Moment of inertia will not change. We can use this for many things, like a drum which is hollow, basically a hollow cylinder. Hollow cylinder, not just for a hollow cylinder, also for a solid cylinder. Also for a solid cylinder. Also we can use this. Let's take this as the axis. This as the axis. Hollow cylinder can be made by stretching exactly what, guys? Think about it. Hollow cylinder, inside everything is hollow. The base and the top is not there. Only curved surface is there. You take a ring and stretch it. You take a ring and stretch it. What will you get? Hollow cylinder. Are you able to visualize this? Exactly. It will come from basically a ring. If you talk about solid cylinder, from which object can you get it? I think you take a disc, full disc, and you elongate that disc. You will get a solid cylinder. So you will get this from basically a disc. So the formula should be same like the ring or the disc. So what will be the moment of inertia of the hollow cylinder? It will be mr square, and the moment of inertia for a solid cylinder will be just mr square by 2. Very good. So this is the formula for a cylinder, hollow or solid. It's the same thing, my dear students. It's the same thing. That's the best part, like the ring or the disc. Useful for many situations. Okay, very good. Yes, Alvin will be doing something very soon. Hold on, bacha. Right. Now that we have learned this property, okay, we need to learn two important theorems which will help us find the moment of inertia in any given situation. In any given situation, we can find the moment of inertia of the body because we know the standard geometries where the ring is rotating about central axis, disc is rotating about central axis. What if it rotates about the diameter? What if a sphere rotates about the tangent? What if it is rotating about some outside axis? So then we need to make use of two important theorems. So let's start talking about them. The first one is called as the parallel axis theorem. The parallel axis theorem. What is this parallel axis theorem? See, if you have some random body, okay, if you have some body, and let's say this happens to be the center of mass of the body, and through the center of mass I draw some axis. This is the axis through the center of mass, and the moment of inertia happens to be ICOM. What is it? ICOM about the center of mass. Some axis is passing. You draw some other axis which is parallel to that axis, either inside or outside, doesn't matter. Either inside or outside really doesn't matter. As long as they are parallel, that's enough. And the distance between them is, let's say, d. So then if you rotate the body about this axis, which is basically parallel, then the moment of inertia about this parallel axis is given by, first take the moment of inertia about the center of mass and then add to it the mass of the body into basically the shift which is there. So this d is also called as the shift of the axis. From here I slid it here, I've shifted it parallelly by d. So this is the final moment of inertia. This is the final moment of inertia about that parallel axis. Don't worry, I will demonstrate this to you by taking some amazing examples. I'm going to take some examples to make you demonstrate and understand this. Okay? So imagine I take a ring. I take basically a ring like this. And usually we know the moment of inertia about this axis. If I ask you, find the moment of inertia about this particular axis, so what will you do? Okay, you have to find the moment of inertia about this particular axis. Well, I will think like this, that I know about the central axis, and the central axis exactly passes through the center of mass. And this moment of inertia through this axis will be ICOM. How much will be ICOM? We just spoke about it. It was mr square. So by parallel axis theorem, this axis is parallel to this axis. I have shifted it by how much? How much is the shift? The shift only is the radius. The shift only is the radius. So this I about the parallel axis will be the moment of inertia about center of mass plus m into basically the shift square. So moment of inertia about center of mass is mr square. How much is the shift? Shift is r only. So it will be basically 2mr square. It will be 2mr square. Is that clear? Everybody with me? Great. Shall we do the next question? Shall we do the next question coming up on your screen? Here it is. Imagine that there is a rod like this, and the rod is hinged over here at the end. The rod is hinged over here at the end. Find the moment of inertia when it is hinged at the end if the rod has a mass of m and length of L. Now again I feel we need to use parallel axis theorem. I'll tell you why. Because I know what is the moment of inertia about this point. So if the rod was to rotate about this point, which was the center of mass, then the moment of inertia about center of mass would have been ml square by 12. Would have been just ml square by 12. Everybody with me? But I don't want to find it over there. I want to find the moment of inertia about this point, about this axis. So essentially, I have to shift it. I have to shift the axis from here to here. One axis was here. I'm shifting it parallelly. Understand, the axis is going in and out of the plane. I'm shifting it from here. I'm sliding it here. How much is the shift? It's not the total length. It's exactly the total length by 2. It's exactly the total length by 2. So the moment of inertia using parallel axis theorem will be ICOM plus m into how much ever the shift is whole square. What is the moment of inertia? Center of mass ml square by 12. What is the shift? It is L by 2 whole square. So this will be ml square by 12 plus ml square by 4. You can take LCM 4 into 3 and into 3 because this will be 12, this will be 12. So ml square plus 3 ml square will become 4 ml square by 12. 12 goes with 4 3 times. So ml square by 3 is the moment of inertia at the end of the rod. Yes, I'll get ml square by 3. Everyone? So this is how you apply parallel axis theorem. Necessarily, one of the axes must pass through the center of mass. Necessarily, one of the axes must pass through the center of mass and the other axis has to be shifted parallel to it. That's why the name parallel axis theorem. Look at this, from here to here, parallel. From here to here, parallel. That's why the name parallel axis theorem. Understood how to apply it? Shall we proceed to the next theorem? Okay, here it comes. Here it comes. That is perpendicular axis theorem. Perpendicular axis theorem. Now this theorem is not applicable all the time. This theorem is not applicable all the time. So imagine you have some lamina. Lamina means a sheet, two-dimensional object. Two-dimensional object. Lamina, sheet, like a plate, disc, ring, rod, right? A cutout of some shape. These are laminar objects. Understood? Now, like the name suggests, perpendicular axis theorem. So there will be some axes which are perpendicular to each other rather than being parallel. So how are these axes? How are these axes? Let's have a look. The first two axes must be in the plane, meaning imagine there is one axis which goes like this. Okay, goes like this, and maybe one thing. Okay, just imagine there is one axis which goes like this. Okay, where you can rotate it like this. About this, the moment of inertia, I will call it as I1. Okay, and there is another axis about which is perpendicular again. If you rotate it like this, the moment of inertia is I2. If you notice, both these axes are perpendicular to each other. I1 and I2 are in the plane. Which plane? Of this object only. They are in the plane. So imagine if I take this, are you able to see this laminar body? Are you able to see this laminar body? One of the axes is in this plane, the other axis is perpendicular to this plane. So if the axis is like this, so if this is the axis, that means I am rotating it like that. So if this is the axis, that means I am rotating it like this. If the axis is like this, that means I am rotating it like that. I am rotating it like this. I hope this is clear about this axis. You draw a perpendicular to that. You draw perpendicular to that. That means the axis is like this. Are you able to visualize it? That means the axis is like that. Yep. You draw a new perpendicular here to both of them, to basically both of them, like that. This is your I perpendicular. This is your I perpendicular, which is perpendicular to the plane itself. This I perpendicular happens to be just the sum of these two moment of inertias. That means I1 plus I2. This is the formula. That's it. This is the formula. It is only valid for laminar two-dimensional sheet-like objects like ring, disc, etc. So you can use this theorem and find out a moment of inertia about the perpendicular axis. Shall we do a question on this so that you really understand how to use this? So let's take up a question, my dear students. Here we have a disc. Okay, so this is our disc. Alright, so this is a disc of mass m and radius r. And the question says, find the moment of inertia about this diametrical axis. Moment of inertia about this diametrical axis. Very interesting question. Diametrical axis. Usually you do not know this axis moment of inertia, you know the central axis which is perpendicular to the plane. No issues, let's try it out. So here is what I think. If this is the disc and I want to find the moment of inertia about this particular axis, which I call it as ID. Think about it. I can also find the moment of inertia about another diameter. The moment of inertia will still be the same. Whether I rotate about this diameter, this diameter, this diameter or that diameter, any diameter is the same. So all the diameters will have the same moment of inertia. Is that point very clear? Is that point very clear? Come on, my dear students. Everybody with me on this? Everybody with me on this? Okay. Interesting thing, I have chosen both the diameters to be perpendicular to each other and they are in the plane of the disc. So that should ring a bell. Maybe I can draw perpendicular to both of them, which is also perpendicular to the disc. So if I draw an axis like this, it will be basically I perpendicular. It's perpendicular to that as well. Oh, that moment of inertia I already know. That moment of inertia I already know. Yes or no? Yes or no, guys? Yep. What is it? It is just going to be mr square by 2. And using perpendicular axis theorem, which says I perpendicular will be nothing but ID plus ID. That means 2 times of ID. And I perpendicular, standard formula for a disc is mr square by 2. Therefore, what must be the formula for ID, guys? Bring this 2 down, it will become mr square by 4. That is the answer. Mr square by 4 is the answer. Yes, Kerry Striker, I will be taking it very soon. I am very much held up with many classes everywhere. Every day I am taking 4 classes. Minimum 6 to 7 hours of teaching is happening. So my throat is giving up. Mentally, I want to take the class. Physically, my throat and my body is giving up every day. So as much as possible, I am coming over here. So I would request the JEE students to watch the NEET channel as of now. As soon as I am clear with the schedule, I will be taking up JEE classes as well. Right? Don't worry, bacha. Cool. So moving on now to another brilliant question. And you will be amazed, mind blown through this question. You will realize the extent till which you can actually use these theorems. The extent till which you can actually use these theorems. Okay? Are you ready for it? Observe. If I take a rod of mass m, length L, and I rotate it about this particular axis, what is the moment of inertia? It is going to be ml square by 12. It is just going to be ml square by 12. Yes? Okay. Now, what next? Imagine I stretch the rod. Imagine I stretch the rod. What will it become? If a rod is stretched, it will become a sheet. It will become a sheet. Okay, so let's turn that rod into a sheet. Something like this. This is length L, this is breadth B. And now still the axis is going to be the same. So the moment of inertia about that axis will still be ml square by 12. Will still be ml square by 12. Everybody with me? Similarly think, had I taken a rod like this of mass m, length b, then the moment of inertia about this particular axis, would have been m, length would have been b, so b square by 12, mb square by 12. So if I stretch it along the axis, again I will get the same sheet. So about this axis, shouldn't the moment of inertia be mb square by 12? Shouldn't the moment of inertia be mb square by 12? Everyone? Awesome. Let's look at it in 3 dimension little bit. Okay, so let's look at it in 3 dimension a little bit. Something maybe like this. Okay, so this is your B, this is your L. This one of the axes is here and the other axis is basically here. This was mb square by 12 and of course this was ml square by 12. Do you see? It's a 2-dimensional object and both the axes are in the same plane. It's a 2-dimensional laminar sheet-like object and they are perpendicular to each other. Something should ring a bell. Which axis theorem will you use? Parallel or perpendicular? Parallel or perpendicular? Obviously perpendicular. Both are in the plane and perpendicular to each other. Perpendicular axis theorem should come into your head. So why not draw a perpendicular axis? So about this perpendicular axis, what will be the moment of inertia? Just the sum of these two. So it will be ml square by 12 plus mb square by 12. Amazing. Amazing. So now I know the moment of inertia of a sheet, meaning something like this. And if I rotate it in this manner, I know the moment of inertia. I rotate the sheet in this manner, I know the moment of inertia is ml square by 12 plus mb square by 12. But I will not stop over there. I will not stop over there. I will pull that sheet and make it into a cuboid. I will pull that sheet and I will make it into a cuboid. Something like this. Look at that. So cool. This is of height h. This is breadth b. This is length l. And this is that central axis that I'm talking about. What will be the moment of inertia about this axis? Same as over here. So shouldn't it be just m by 12 L square plus B square irrespective of the height? Stretching property I have used, using stretching property. So now I know the formula for moment of inertia of a cuboid. The best part is just from a simple rod, pulling it, perpendicular, pulling it, I get the moment of inertia of a cuboid. Shows how you can visualize. Right? To solve a problem, visualization is very, very important. Yes. Hello, Jameshni. Clear? Understood? Oh? Shall we move ahead? Perfect. Right? All right. So, let's solve one more question. Let's solve one more question before we go ahead. Okay? And then probably we can, go to the last part of moment of inertia. All right. Chalo, let's see if you guys can solve this. This is a disk. This is basically your disk. The disk has a mass of m and radius of r. And the question is, you take a tangent and you rotate the disk. Question is, find the moment of inertia about that tangent. Find the moment of inertia about that particular tangent? That is the question. That is the question. Let's think. The moment you look at it, there is no standard formula for moment of inertia when a disk is rotated about this tangent. So I need to think of some transformation, shifting, tilting the axis some way or the other. So here is what I think. If this is the disk, this is the center, the tangent will be basically something like this. And you have been asked the moment of inertia about this tangent. I can do one thing though. I can draw an axis parallel to this, and if I know the moment of inertia about this axis, I can shift it from here. I can shift it from here to here, all right, by a distance of r to find this moment of inertia. But there is a problem. The problem is I don't know the moment of inertia about this axis, because this axis technically is the diametrical axis, is along the diameter. And I know the moment of inertia when the axis is like this, in and out of the plane of the board. In and out. If it is like this, then I know. Oh, I know about this axis. I want to know about this axis. They are perpendicular. Maybe perpendicular axis theorem. So why not take another perpendicular axis like this? Why not take another perpendicular axis like this? This is also the diameter. This is also the diameter. This is also the diameter. Both are in the plane of the disk. The final perpendicular to their plane will be like this. This only. This axis. This is the moment of inertia about that perpendicular to the plane. See if you are able to understand the transformation. From here, if I want to find this, I need to find this. To find this, I need to find this and this, because these two are perpendicular in the plane of the disk. So that will come through the central moment of inertia, which is perpendicular to the plane. So there are multiple theorems that I will have to use. First theorem to start with is the perpendicular axis theorem will be equal to the moment of inertia about the diameter plus moment of inertia about the diameter. So this was your perpendicular axis theorem. So this will become just 2 times of ID. What is the perpendicular moment of inertia? This is about the central inertia, normal formula for a disk. The normal formula is mr square by 2. Okay, so from this I am getting the moment of inertia about diameter is mr square by 4. I'll keep it sideways. I'll just keep it on the side. Now let's talk about this guy's moment of inertia. The moment of inertia about the tangent, will be moment of inertia about the diameter plus m into the shift square. So moment of inertia about the center of mass, which is moment of inertia about the diameter, right? This is about the center of mass, and this is the shift square. So this is your parallel axis theorem. Everybody with me? Very nice. So what is this? I just figured it out. It was mr square by 4. What is the shift? The shift is r. So it will be mr square. 1/4 plus 1 is 5/4. 5 by 4 times of mr square is the moment of inertia of the tangent. So this is how you solve the problem, by combining perpendicular with parallel axis. So this is the variety of questions that you can get, in the NEET examination. Be it a disk, be it a ring, all right. Sometimes you might be given a question like this, where there are just 2 spheres like this, touching each other. 2 spheres, they are touching each other. And let's say the axis given is like this. And the question will be, find the moment of inertia about this axis, and both of them are solid spheres of mass m and radius r. How do you find it out? Both these spheres are rotating like this. Okay? Both these spheres are rotating about their common tangent. Well, think about it. If you know the moment of inertia of any one sphere about this axis, you multiply it 2 times, you will get the total moment of inertia. You know anyone? Multiplied by 2, you get the total moment of inertia. Yes or no? Very good. So let's do that. If you take any one of the solid sphere, and if we are talking about this particular axis, it's not passing through the center. It's not passing through the center. In fact, only when it passed through the center, I knew the moment of inertia. Only when it passed through the center of mass, I knew the moment of inertia was 2 by 5 mr square. In fact, I had to shift it by a value of r. So the moment of inertia about this parallel axis will be moment of inertia about center of mass plus m into basically the shift square. What is moment of inertia about center of mass? 2 by 5 mr square. What is the shift? It is mr square. 2 by 5 plus 1, 2 plus 5 is 7. So 7 by 5 mr square is the moment of inertia about this parallel axis for a sphere. That's it. But this is for a sphere. There are two spheres. So, my dear warriors, what will be the total moment of inertia which is being asked? It will be nothing but 2 times the moment of inertia whatever you have found over here. So that will be 2 into 7 by 5 mr square. That means 14 by 5 mr square. So that is the final answer. That is the final answer. Everyone, very good Karthik, very good Priyanka, amazing go. So these are some amazing questions of how to use properties theorems to find any systems or bodies or a combination of bodies moment of inertia. That's all. Now there is one more thing in moment of inertia, very rarely a question might come on it, and that is called as the concept of radius of gyration. Radius of gyration. Gyration means rotation. Gyration means rotation. So something related to rotation. So what is this radius of gyration? What is this radius of gyration? So if you take a body, let's say the moment of inertia is I about this particular axis, you melt that body. You take the same axis. And when you melt it, make it like a point mass. Whatever body was there, whatever that body was there of mass m, you melt it into a point mass. Whatever inertia it had here, make sure this mass also, when it rotates, has the same inertia. Meaning, you choose the distance appropriately. That distance is called as k. That k is your radius of gyration. So it's that distance, it's basically, that distance where the concentrated mass has same moment of inertia as of the body. So this moment of inertia is I. This moment of inertia is m into k square. So when these two are equal, that radius, that distance k is called as the simple radius of gyration. Let me give you an example. After that you will be like, oh sir, this is so easy. If I ask you, find radius of gyration for a hollow sphere. What will you do? See, if you take a hollow sphere, what is the moment of inertia? It is 2 by 3 mr square. I want to convert it into a point mass, m. What distance will I place it at? K. So mk square is that moment of inertia. This should be equal to 2 by 5 mr square. That is the moment of inertia of the hollow sphere. Sorry, not 2 by 5, 2 by 3. 2 by 3 mr square. It's hollow. Mm cancels. k square will be 2 by 3 times of r square. So k will be r times root of 2 by 3. That's it. That's the answer. So at this distance, when the mass is placed, it has the same behavior or inertia as that of the hollow sphere. Same behavior. Same way, if I ask you, find K for a solid cylinder. K for a solid cylinder. What will you do? Again, start with the same thing. Moment of inertia of a solid cylinder is mr square by 2, like a disk. And this mass has to be concentrated at a distance of k. So point mass's moment of inertia is mk square. So equate this with mr square by 2. Cancels. K will be r by root 2. That's the radius of gyration. Everybody with me? Understanding how to solve these kind of questions for radius of gyration or in general finding moment of inertia? These questions are very common. Okay? Very common. So that is the first part. So at least one question, 4 marks is guaranteed now. Okay. Cool. Now, imagine from mass, we go to the next subtopic, which is going to be called as torque. Okay, after mass or inertia, all right, moment of inertia, we go to the next subtopic, which is torque. To understand torque, here is how I look at it. I will compare it with translation and then I will go to rotation. It will be very easy. I will compare it with translation, which you already have studied, and then it will be very easy. I'll tell you how. See, if you take a mass and you apply some force on it, it changes its state of motion. Basically, it accelerates. This force is also called as the cause. This mass is your inertia. This acceleration is basically the effect. And we know, according to Newton's law, the net force is the mass into acceleration. This is your Newton's laws of motion, but for translation. Correct? So you take a mass, you apply a force, it changes its state. That effect is acceleration. Force is the reason, it is the cause. How much the effect will be there depends on this inertia. If the mass is more, acceleration is less. If the mass is less, effect is more, acceleration is more. That's all you get from translation. Now, is there an equivalent for all of this in rotation? The answer is yes. Let me remind you, just like you have velocity, you have something called as angular velocity. Angular velocity, we have discussed this in circular motion. Omega is d theta by dt. What is this d theta? It is basically a small angular displacement. Small angular displacement, if you remember carefully from circular motion. This omega is always expressed in radians per second. You can also convert it into degrees per minute or degrees per second or rounds per minute and all of that. Correct? And there was a relationship between a particle which was going in a circular path with some velocity v having a radius r and the angular velocity omega. What was the relation? Omega was v by r. Do you remember this? Or basically v was omega into r. We have seen this in circular motion. Everybody remembers this? This was your tangential velocity. Tangential velocity, if you remember carefully, for a particle going in a circular path. Similarly, the next term that we had studied was called as angular acceleration. Symbol for that was alpha. Alpha was how quickly omega is changing with respect to time. D omega is a small change in angular velocity. Angle wise, how much the velocity has changed. It was slow, then it became fast, or it was fast and then it became slow. So that is angular velocities change with respect to time. you get angular acceleration expressed in usually radians per second square. And similarly, if there was a particle going with some tangential acceleration at in a circle of radius r, then the angular acceleration alpha, if you remember, was at by r, or the tangential acceleration was alpha into r. We have seen this. A tangential was alpha into r. Do you remember this? Everybody with me? Clear? Just like over here, we had this for the tangential acceleration. Now this alpha is also called as the effect of rotation. Is also called as the effect of the rotation. Cool? Okay. So let's see what it means. Imagine you have some body, okay, and there is some axis about which it can rotate. There is some axis about which it can rotate. This body has its own moment of inertia. I will call it as I. This has its own moment of inertia. All right. So it has its own moment of inertia, which we can call it as I. If there is an effect, meaning there is some kind of angular acceleration, velocity is changing, it is slow, it moves faster, then just like over here, if there was an acceleration, there was a force, same way, my dear warriors, if there is an angular acceleration, then what must be there is basically torque. What must be there is basically torque. So strictly speaking, torque is the rotational cause. Rotational cause. This is your rotational inertia. Rotational inertia. This is your rotational effect. Rotational effect. This is your rotational effect, which is basically your alpha. So I can say this is alpha. Instead of inertia, mass, I have I, and instead of force, I have the rotational cause, which is called as the torque. Torque is equal to I alpha is the equation very similar to F is mass into acceleration. Instead of force, you get torque. Instead of mass, you get moment of inertia. Instead of A, you get angular acceleration, which is the rotational effect. So torque is the equivalent of force in rotation. Is the reason why a body begins to rotate or stops to rotate or changes the speed of rotation some way or the other. So torque is the cause of the rotational change of state. So this is basically now your new equation. I can again call it as Newton's law of motion, but in rotation. But now in rotation. Amazing, right? The similarity, the resemblance is amazing. This, remember, is always called, this is always the net torque. This is always the net torque, just like over here. This is not a single force. This is always going to be the net force. This is always going to be the net force acting on the body. It is never going to be the one single force. Same way, this is always going to be the total torque acting on the body is the inertia into the effect, which is alpha, angular acceleration. Amazing. This is amazing. Now, in normal Newton's laws, what you used to do, you used to draw the free body diagram. mg, normal, tension, spring, blah, blah, blah. And then you used to find the components of the forces, x component, y component. Oh, these forces are in the x direction. It is also moving in the x direction. Or this force plus this force minus this force plus this force minus this force is mass into acceleration. That's all. But in rotation, there is one extra step. In rotation, there is one extra step. You can't just show the FBD and say, oh, I'll split the forces and done, and I'll do I into alpha. No, you cannot do that. The problem is torque can't be just written down so easily. Even if you know the force, you need to know where the force is acting. What did I say? Where the force is acting needs to be known. Only then you can find the torque. So what is the way or the manner in which torque is found? What's the formula for the torque? Let's see that next. Then we will use this equation. Alright. So let's talk about how to find torque. Like we had a movie called as Finding Nemo. So now this is finding torque. Let's try to find the torque. Now whenever this topic comes, I have seen all the doors in the classroom, they start crying and they start saying, oh, now my turn has come. Because this is the, fate of all the doors in the classroom by the hands of a physics teacher whenever the topic of torque comes. Poor doors get used, but you cannot see the door over there. It's out of the screen, right? So I will make use of this poor pad which I have, and I'll try to explain the torque. So let's say I'm holding this here. Do you see this is the axis? This one over here, this one over here. I can rotate this like this. Okay. If somebody comes, I can just smack them down like this. Thap karke. Okay. Everyone with me? Yes. Circular motion, Sona is already done long time back. Okay. So it is basically like this. It is rotating. Now imagine I tell you, you have to rotate this body. Will you, by common sense, apply the force here or here? Where do you think it will be easy to rotate it? Where do you think you can apply the force and it will rotate more? If you apply the force here, you need a large force. It will take a lot of effort. If you apply the force here, it takes less effort. Oh, so where you apply the force from the axis matters. Here it is much easy. It is much easier to rotate. Whereas here it is little difficult. Here it is even more difficult. On the axis, if you apply the force, then it will not rotate. On the axis, it will not rotate. Only here it will rotate. Everybody with me? Okay, very good. Not just that. If at the same place I apply more force, it will rotate more. More cause is there if there is more force. So one thing for sure, it depends how far from the axis. Second thing for sure, how much the force is. It will rotate more. If the force is less, it will rotate less. One more thing, third thing is the angle. If I apply the same force here like this, it will rotate easily. But if I apply the force like this, why will it rotate? Or at an angle like this, the force will not produce so much of a rotation. So the angle also matters. Alright, so can I say that the torque depends on three things? The location, or basically the point of application of the force. Second thing, it depends on the force itself. And the third thing, the direction of the force. This is the force magnitude, direction of the force. All these three things together decide how much the torque is. So if this is a body over here, and let us just say this is the axis, okay, and it so happens that I am applying the force in this particular direction. This force is at some distance from here. Let's take this distance as r. It's at a distance r. So point of application of force, basically r. Magnitude of the force, basically that f. Direction of the force. So for that, just extend this line and just mark this angle. I'll call this theta. So basically theta. It depends on all these three things. Everyone with me? Now, out of this force, if I split the force into two components, one force perpendicular, basically maybe something like this. Okay, just try to visualize this in 3 dimension. Okay, it's a little difficult, I know, but try to visualize this. This is perpendicular, and other component which is like this, other component which is like this, parallel to R. This parallel component which is F cos theta, and this perpendicular component which is basically F sin theta. Out of these two, who do you think will cause the rotation about this axis? Who do you think will rotate it? Will F parallel rotate it? F cos rotate it? No, F cos will pull that object out of the axis. It will not rotate it. Rotation is because of that perpendicular component. So you can basically say that the torque, symbol for torque, by the way, like I had told you, is tau. The torque is proportional to 3 different things. One is, how much is your actual force? How much is your actual force? And it also depends on the sine theta component of the force, not F, but the sine theta component. And last thing, how far you are from the axis also decides the torque. More R, more torque. Farther you are, more torque. More force, more torque. More the angle, that means this perpendicular component. So sine theta what matters, so that increases the torque. So removing this proportionality, converting it into an equality, the magnitude of the torque will be F sine theta into R. F sine theta into R. That's all. Everyone with me? Everyone with me? Okay. Right. To join Unacademy, guys, there are links in the description box. You can join through that. And the best part is you have some amazing things which are going to continue in the next few months. There are crash courses, there are test series, there are amazing lectures by me and the entire team. So we would have a lot of fun. In fact, there are some special classes which are going to be conducted just this week alone. So make sure you're a part of it and make the best use of the offers by using the code CAPTAIN, CAPTAIN. So that's the code which you'll be using for getting the best of the best offers for any subscription, for any crash course, for any test series. Cool? All right. It should be scheduled, Gautam, very soon. Don't worry. Okay. Now, F is a vector, R is a vector, even torque is a vector. Actually speaking, torque is nothing but the cross product of, or the vector product of the position vector and the force itself. This is the way in which you actually define torque. Torque is R cross of F. So remember the cross product. First take the 4 fingers of your right hand in the direction of R. In the direction of R. These 4 fingers in the direction of R. Slowly bend it towards the force. The force is that way. The force is that way. So bend the fingers like this. Bend the fingers like this. You will see the thumb of your right hand automatically points up. Automatically points up. So exactly that's the direction in which the torque exists. So the torque is in this direction. That's all. That's how you find the direction of the torque. Now many people find it hard to believe torque is this way. I'll tell you a simple explanation for that. Imagine I tell you, okay, listen, the torque on a body is this way. The torque on a body is this way. You will immediately think torque is that way means using right hand rule, the thumb would have come in that direction. The thumb would have come in this direction. So the fingers would have curled in this particular manner. The fingers would have curled in this particular manner. If you point the thumb in this direction, so put the thumb in this particular direction, you will see the fingers of your right hand will curl in this particular direction. In this particular direction, everybody. So this is how your fingers will curl. So this is the sense. This is the sense of the direction of the torque. This is how the torque will basically act. This is how the torque will basically act in this way. This is the best way to immediately see what is the direction of rotation. You will be like, sir, you could have done this simple thing. No, clockwise and anti-clockwise. Why all this nonsense business, sir? Why all this right hand and all these things? We can just say clockwise and anti-clockwise. Okay, I'll tell you what is the problem with clockwise and anti-clockwise. Okay, just look at my hand. Just look at my hand. How do you think it is moving? How do you think it is moving, guys? How do you think it is moving? For you guys, come on, answer in the chat box. How do you think it is moving? Clockwise or anti-clockwise? How is this hand moving? Clockwise or anti-clockwise? Everyone, start putting up the answers. Start putting up the answers. Is it clockwise or anti-clockwise? Come on. Come on. Come on. Think about it. Yes. Is it clockwise for you? Is it clockwise for you? Very good. You know how it is for me? From my perspective, I will not do anything, but I will show you how it looks for me. It looks anti-clockwise. For me, it is anti-clockwise. But the same thing for you is clockwise. So there is a confusion. When I say clockwise, from which direction? This way or that way? Hai na? So that creates a confusion. So that's why we create a very unique way of representing the direction by using the right hand thumb rule. Okay, so always pointing the thumb in the direction of the torque gives me the sense of rotation by looking at the curled fingers. By looking at the curled fingers. As simple as that. I hope this is clear. Yep. Don't worry, Gautam. That's why there are problem solving sessions like the one which I am conducting in the special class this week. So apart from my theory classes, and if you are a part of the Energize batch, the Avenger batch, there so we do so many practice questions, so many variations, and these problem solving sessions, this will be more than enough apart from the self-study that you do to crack NEET with 180 out of 180 in physics. I am guaranteeing you that. I won't give you 1 mark less also, I will give you only 180 marks. Okay, so that's how you find the torque. Similarly, if I tell you that listen, this is where R is, okay, and this was our axis, and let's say our force was in this particular direction. Our force was in this particular direction. Can you guys quickly guess and tell me which direction is the torque? Which direction is the torque? Come on, quickly think and tell me. Is it up or down? Come on, do R cross F. R is this way, force is that way. You can't bend your fingers like this. You can't bend your fingers like this. So turn it upside down. Turn the hand, the right hand upside down. R is like that. F is here. R is that way. F is here. So your thumb should be going down. So immediately you should be able to sense this, that the direction of the torque is in this direction. Direction of the torque is in this direction, downwards. Very good. In many other scenarios also, we can immediately guess the direction of the torque. Say for example, this is the axis and this is a body over here. And I tell you, listen, there is a force acting over here. There is a force F1 acting over here. In what direction will it create a torque? About this axis. Think, what will this force do to this body? It will pull it. You pull this body up, it will rotate like that. So 100% it will create an anti-clockwise torque. If you see it from this side, it will create an anti-clockwise torque. Everybody with me? Similarly, if I apply a force like this, F2, okay, on this body, see what will happen because of this particular force. This body will rotate like this. It will rotate in the clockwise direction. So this will create a clockwise torque. This will create a clockwise torque. Similarly, if I apply a force in this direction, F3, think what will happen because of this force on this body. This body will be pulled like this. It will rotate like this. So hence, it will create a clockwise torque. Similarly, if I apply a force like this, F4, see what will be the direction of the torque. This F4 will rotate this body like this. So it will create an anti-clockwise torque. But if by chance the force acts here, and that is F5, then it can't rotate the body. It can't rotate the body. Then the torque will be zero. Torque will be zero. It can't rotate the body. Not just that, if by chance along this line I apply a force here called as F6, even that F6 is along that line, it can't create any torque. It can't create any torque. Same way, if I apply a force like this called as F7, but it is directed towards this axis, 100%, it will not create any torque. All these forces will not create torque. If the force passes or appears to pass through the point, it can't rotate it. It will just push against or towards the axis. So it can't rotate. It can't cause any rotation. Is that clear? Is that clear? Everybody with me? All right. So that's how you measure the torque's direction. Now, there are more than one ways of measuring the magnitude of the torque. Let me show you that. Very, very interesting phenomena. So, if this is the axis, this is the axis. I'll show you these amazing techniques. This is your position vector where the force is located. This is the position vector where the force is located, and this is your force. The force can be split into two components. One component like this, which is F perpendicular, which is also your F sine theta. All right. The other component you will not even bother, because that will not create any torque, and the torque over here will be created like this. Correct. Same way, that same force is applied here. Same force is applied here. I will not split the force. I'll tell you why in a bit. Remember, I just told you that the torque magnitude is nothing but your R into basically F sine theta. R into F sine theta. Correct? Now this F sine theta, I can write it as F perpendicular also. I can write it as the perpendicular component of the force also. So this is R, and this is basically your torque. So torque is R into F perpendicular. This is one way of writing it. This is one way of writing or measuring the torque. Now observe this. If I pull the line of the force, this is called as the line of the force, then I can drop a perpendicular over here. You can very well see that this was theta. So this will be theta. This is hypotenuse. In this right angle triangle, this is hypotenuse. This will be R sine theta. I can call this as the perpendicular distance on the line of the force. So why not write R sine theta together? If I write R sine theta together and that if I multiply it by the force, I will get the torque again. So why not write it as R perpendicular into F. R perpendicular into F. This is also correct. This will also give you the torque. It's up to you whether you want to use this or this. Like while measuring work, it was force in the direction of displacement into displacement, or force into displacement in the direction of the force. One and the same thing. F into S cos theta or F cos theta into S will get the same answer. Same way, torque is R into F sine theta or R sine theta into F. One and the same thing. When I write F sine theta, it means the perpendicular component of the force. When I write R sine theta, it means the perpendicular distance of the perpendicular distance on the line of the force. That's all. One and the same thing. Right? Remember, R cross F will not be useful unless the question or the data is given in I, J, K. Understood? Understood, Kushal? Every time R cross F will not be useful. Why do you think the data will be given in I, J, K every time? Very rare. Usually the question will have some forces, etc. like this free body diagram, and that's how you will solve the problem. Correct? So be careful about it. Yes, I will be making a video. Don't worry, guys. Cool? Let's go ahead and look at some questions. Let's go ahead and look at some questions. Here is a question, amazing question. This is a disc. Okay, it is like this. And this disc has a mass of 2 kg and let's say 0.5 meter radius. What happens is, on this disc, along the tangent, somebody applies a force of 10 Newton. Along the tangent, they apply a force of like tuck, 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 somebody spinning it. It starts spinning. Okay. This disc basically starts from rest. Starts from rest. And somebody starts applying this force. So because of that, obviously it will gain some angular velocity. So the question will be, find omega after let's say 10 seconds. That's the question. Find omega after 10 seconds. Now in this question, when this force is applied of 10 Newton, what will it create? Rotation wise, it will create a torque. It will definitely create a torque. That torque creates angular acceleration alpha. Can we first find the value of the torque? I think so. It's not so difficult to see that on this disc, this is the radius, which is basically 0.5 meters, and the force is applied here, which is basically 10 Newton, and that is already perpendicular to the distance. So the torque, can I not say, will be R into F perpendicular, R being 0.5 meters into force being 10 Newton already. I don't even have to take sine or cos or anything for that matter. Okay, so that will just give me 5 newtons into meter. That is the unit of torque. 5 newtons into meter. What does a torque do? It creates alpha. Oh, to find alpha I need I. Do I know the value of I? I think so. The moment of inertia, this is a disc, is mr square by 2, mass 2, radius 0.5, square by 2. So 2 cancels, 0.5 square will be nothing but 0.25 kg meter square, or basically 1 by 4. So now we know what is the next step that I will be doing. Remember, torque is equal to I into alpha. Torque is equal to I into alpha. I need alpha to find this. If I know acceleration, I can find the velocity. What is the torque? It is 5. What is I? It is 1 by 4. It is 1 by 4 into alpha. So from this, what is the value of alpha, guys? 5 4s are 20 radians per second square. I got the value of alpha. Awesome. But that's not the end of the story. Remember, we used to have an equation like V is U plus AT. Same way we have an equation here. Final angular velocity is initial angular velocity plus angular acceleration into time. This is like kinematics, but in circular motion, correct? So what will be the initial angular velocity? It starts from rest, so 0. What is alpha? That is 20. What is the time? Time is basically 10 seconds. So what is the final angular velocity? 200 radian per second. That's it. That is the answer. Very good. That's the correct answer. Understood, guys? How to solve a question of torque, alpha, moment of inertia, how it is used in a problem. This is a very nice example, simple one to demonstrate that. Let's take one more example over here. Imagine that there is a hinge over here and there is a rod, something like this. All right. So this rod has a mass m and length L. It is left from rest. Question is find alpha. Question is find alpha. That's all. The rod is left from rest. Find alpha. Okay. So now you might be thinking, what do we do now? I would say draw FBD. Just like to find acceleration, what do you do? Draw FBD. Same way. But be careful. Don't show the forces randomly anywhere. Show the forces exactly at the points where they will be acting. So in this case of the rod, what are the forces that might be there? One mg will be there, everyone. Mg, gravity will be acting through the center of mass. There could be a normal force also. Nothing else. And this mg will act from the center of mass. Apart from that, this rod will also rotate. When you leave it, it rotates. So 100% there is angular acceleration. The center of mass will come down. So there is also the acceleration of the center of mass. The center of mass will come down. So there is acceleration of the center of mass. Okay, now how do I find alpha? To find alpha, I am just going to use that the net torque should be moment of inertia into alpha. Maybe I can find the torque very easily. Look at it. About this axis, is the normal force giving any torque? Is the mg force giving any torque? Just tell me that. Is the normal force giving any torque? No, it is passing through the axis. How can it give torque? R is only 0. How will it give torque? So the torque by the normal force is a big fat 0. Torque is a big fat 0. Everyone with me? Awesome. mg is acting at a distance of L by 2. Oh, look at that carefully. mg is acting at a distance of L by 2. That is basically your R, and that is perpendicular. So remember, torque was RF perpendicular, RF perpendicular, RF perpendicular, or R perpendicular F. So over here, this is R, which is basically L by 2 into perpendicular force itself is mg. And which direction is the torque? This force will rotate it clockwise. It will rotate it clockwise in the direction of alpha, which is also clockwise. That's why I will use plus. If by chance the force was that way, no, I will use a minus sign. It will be against alpha. If it is in the direction of alpha, positive. It's opposite to alpha, not with it, against it, so minus sign. In this case, it is with it, helping it, so plus sign. It is clockwise. See how this force is rotating it clockwise as the rod rotates. Okay. Now this I, this is moment of inertia of the rod, but at the end, not at the center. So guys, you will have to shift the moment of inertia using parallel axis theorem. ml square by 2 plus ml by 2 whole square, guys. This is using parallel axis theorem. We had done this question just some time back. Do you remember this? Exactly. And what was the answer that we got? We got it as ml square by 3. If you remember, ml square by 3. If you want, you can solve this and see. You will get it as ml square by 3. Now many things will get cancelled also, like this L, this L, this M, this M. That's it. So I'll be left with the value of alpha now. So alpha will be 3g by 2l. Exactly what we wanted. 3g by 2l. Understood? Everyone with me? Same way, you can also solve any question where pulley has mass. I'll give you an example. Imagine this one over here, this pulley is hanging like this. This pulley is like a disc of mass, let's say 2m, radius r, and over here there is a point mass or a block of mass m, and let's say over here there is a mass of 3m. The question will be find the acceleration. Find the acceleration. Now, usually what used to happen in these kind of questions in regular Newton's laws, we will take one more lecture, Krishna, for rotational motion, that's all. Usually what we used to do, we used to show the weight here like 3 mg, correct? Then another weight here, which is basically mg. This 3m being heavier will come down with some acceleration. M being lighter will go up with some acceleration. There will be also one tension over here. There will also be some tension over here. This is how we used to draw the FBD and write the equations and solve it to find A. But you can't do the same thing now. I'll tell you why. The problem is, earlier, if it was a light pulley, meaning this pulley itself has no mass. If this pulley itself has no mass, then the string which is wrapped over it, okay, will have a tension from here and a tension from here. These both tensions, look at it, it is trying to create a torque. This tension trying to rotate it clockwise, this tension rotating it anti-clockwise. Yes, this tension rotating it clock, this tension rotating it anti-clock. The moment of inertia itself is 0, no matter what the alpha is. So the net torque must be 0. The net torque must be 0. How can the torque be 0? Only if both the tensions are equal. So basically, the tensions are essentially the same on both the sides. But when it is a heavy pulley, then you cannot take the tensions the same. In fact, the pulley itself will have some alpha. The pulley itself will have some moment of inertia. Here, the moment of inertia was 0. So here I would say moment of inertia into alpha will be the net torque. So if there must be net torque, one tension must be more than the other, because one tension will create a torque this way, other tension will create a torque this way. So this will be like T1 and T2. So tensions are basically going to be different. Did you understand this? Tensions are going to be different when there are heavy pulleys. So it is wrong to put TT. This will be T1, this will be T2, or this is T1, that is T2. It's okay. And you will alternatively also have to draw, okay, T1 here, T2 here. Yes, there will be 2 mg over here and a normal here and angular acceleration here. This is the complete FBD. Why normal? Because that support will be pulling that pulley. That's why a normal from the roof, it will be holding it. 2 mg because that mass of the pulley will have its own weight. T1, T2, different tensions. And alpha because if this goes down, this goes up, the pulley will rotate clockwise. If this goes down, this goes up, the pulley will rotate clockwise. Clear till this point, everyone? With me on this? Pakka? Awesome. So let's write down the equations. How will it look like? For this guy, for 3m guy, how will it look like? This is bigger force, this is smaller force because it is going down. So bigger force, which is 3 mg, minus smaller force, which is T1, is equal to mass into acceleration. This is equation number 1. Equation 2 for this guy, small m, is going up. Big force, small force. Big force T2 minus small force mg will be m into a. Equation number 2. Then for this guy, the pulley, normal will it give torque? 2 mg will it give torque? Think logically. Yes or no? Come on, put it up quickly in the chat box. Normal is acting through the axis. Weight is also acting through the axis. Will it give torque or will it not give torque? Think about it. Obviously, it will not give torque. Because R is 0. only T1 and T2 will give torque. Only T1 and T2 will give torque. So torque by normal 0, torque by weight 0. Torque by T1, look at it guys quickly. T1 is at a distance of r, even T2 is at a distance of r, both of them are perpendicular. This T1 is helping alpha. This T2 is against alpha, because this T2 will rotate it like that. This T1 will rotate it like this, helping alpha. So T1's torque is positive. So I will put plus R into T1. Why plus R into T1? T1's torque is clockwise in alpha's direction. Okay. T2's torque is opposite to alpha. T2's torque is opposite to alpha. So minus. So minus R T2. Why this into this? R into F perpendicular. R into F perpendicular. R into F perpendicular. R into F perpendicular. That's why. Okay. Is equal to I into alpha. Now what is moment of inertia for a disk? Everybody quickly think and tell me. It was 2m into r square by 2. Why 2m? Because the mass of the disk is only 2m. Actually it is mr square by 2, but here m only is 2m. What is alpha? What is alpha? Come on, my dear students. What is alpha? Just like over here, if you have a pulley, let me just put it over here. If you have a pulley, this is the string. If this point of the string is accelerating with A, even this point of the string is accelerating with A. This point is going with tangential acceleration, and tangential acceleration is alpha into r. So whatever this A is basically the tangential acceleration only. Means it is alpha into r. Alpha being the angular acceleration. Oh, so basically alpha is A by r. Alpha is A by r for a pulley. Everybody able to see that? So why not substitute alpha as just A by r? Just as A by r. So over here I will have r into T1 minus T2. Many things are going to get cancelled, like this r and this r, this r and this r. Oh, very nice. So I will be left with T1 minus T2. 2 will also cancel. It will just become Ma. This will be my third equation. This will be my third equation. Do you see? T1, T2 and A. 3 unknowns. 1, 2, 3. 3 equations. Solvable. Solvable. How to solve this? How to solve this? Just add all of them. Just add all the equations. If you add all the equations, see what will happen. This minus T1 will get cancelled with this T1. This plus T2 will get cancelled with minus T2. So you will be left with 3mg minus mg and nothing over here is equal to, here you will have 3ma plus ma plus ma. So 3mg minus mg is 2mg is equal to 3 plus 1 4, 4 plus 1 5. So 5ma, m cancels. So a will be 2g by 5. So a will be 2g by 5. That's the answer. Got it, guys? This is how you solve a problem where the pulley itself has a mass. Where the pulley itself has some mass. Amazing. Now there could be some questions where you might not have to use torque is equal to I alpha. We saw some questions where torque was I alpha. Torque was I alpha. Over here also. Torque was I alpha. Instead, you might find that the net torque might be 0. You might find the net torque might be 0. Those problems are called as the problems of equilibrium. Equilibrium. Meaning there is some body, okay, and there are multiple forces acting on it. There are multiple forces acting on it like this, okay, multiple forces acting on it. If I add all the forces and I find that it is 0, then I will say that it is in translation or translatory equilibrium. If all the forces cancel, then there is no translation. But if I measure the net torque and it is 0, I will say that it is in rotational equilibrium. That means it is not rotating. Sometimes a body will be not rotating, but it will be just translating, like a block sliding down a slide or a incline. It is not rotating, it is just sliding. So there is translation, no rotation. Sometimes the wheel will be spinning on its own at the same place, like your fan. So there is no translation, but there is rotation. The vehicle which is moving on a road, you will see the tire not only spins but also translate. So there will be translation as well as rotation. A rock on the mountain which is not yet moving, it's just there, it is in equilibrium. There is no translation, there is no rotation. So that is said to be in equilibrium. That is said to be in equilibrium. Is that clear, my dear warriors? What is the meaning of equilibrium? There is no torque, there is no force. All right. One such equilibrium is called as the couple force. Is called as the couple force. Our favorite couple is Pandu Champa. Always fighting with each other. They are very similar but always opposite. I want to go for this movie. Champa says I want to go for that movie. Pandu says I want to eat pizza. Champa says I want to eat ice cream. Okay, they are all equally hungry, but they are opposite. Same way, a couple force means two forces which are equal and opposite. Basically, equal and opposite forces. In such a case, what will be the net force, guys? F that way, F this way. Obviously, it will cancel, right? F minus F, it will be a big fat 0. So the net force will always be 0, but net torque will not be 0. I'll tell you why. Imagine these two forces, they are being separated by a distance of L. These two forces are being separated by a distance of L. You measure the torque about this point. Then when I calculate the torque, when I calculate the net torque, for this force, which is perpendicular from here, this distance, how much will it be? Won't it be L by 2 from here till here? L by 2. Perpendicular force is F. So what is the torque by that force? Won't it be like this? Won't it be L by 2 into F? L by 2 into F is the torque. Same way, this force is again at a distance of L by 2 only. This force will also give a torque in the same direction. In the same direction. So another torque, L by 2 into F. You will see L by 2 plus L by 2 is L. So it will be L into F. So the net torque, my dear students, is not 0. This is the speciality of a couple force. This is the speciality of a couple force. There could be a question where a body is in equilibrium and you have to find something about that equilibrium. Like, say for example, imagine this string and this string together, which are hanging from the roof. They are supporting a rod. Okay, so the rod has a mass of m and length L. Another point mass is stuck over here whose mass itself is 2m, and this distance is given to be L by 4. Question is, if this tension is T1, this tension is T2, question is find the tensions. Find the tensions. Very, very common kind of question which can be asked on equilibrium. This rod is at rest. It's not rotating. Equilibrium. It's not translating. It's in equilibrium. So I can use these concepts. net force is 0, net torque is 0. So let's try that out. Start with FBD. Without FBD you can't do much. So let's start with the free body diagram. What are the different forces? Well, from this side there will be a tension T1. From this side there will be a tension T2. Both these tensions will not be equal, but they will be upwards. Why they are not equal? Because this mass is slightly on this side, so it's not symmetric. So that's the reason why one tension will be more, one will be less. Then this 2m is a point mass, so there will be a 2 mg weight over here, and this rod itself has a mass m. The rod's center will be here. This rod's center will be here, so there will be a mg force also over here. Oh, amazing. Now this is the complete FBD. I know acceleration is not there, angular acceleration is not there. Basically it is in equilibrium. So what I will do, if it is not accelerating, all the forces must cancel each other. So can I say the net force is 0. So therefore upward force T1 plus T2 will be downward force, which is mg plus 2 mg, meaning that is 3 mg. So that is basically your T1 plus T2. Okay, perfect. Now what? Next, I will also use, because there is no angular acceleration, can I also say net torque is 0? Oh yes, but at which point? Let's take about this point. Actually, you can take any point. But choose a convenient point. Because no matter which point you take, total torque will be 0. It is not rotating, no? About this point, that point, that point. Or this point also it is not rotating. Or this point also it is not rotating. Why then did I choose this point? It is convenient. How do I know it is convenient? Because when I measure the torque about this point, this force which is there, no, that will not give only any torque, because it is passing through the point. So it has no contribution only in the torque. Amazing. So the torque by tension 2 is 0. The torque by tension 1, check this out about this point. This tension 1 will rotate it clockwise. See this, T1 will rotate it clockwise. So I'll use it as plus. Distance is L. So L into perpendicular force is T1. So that is clockwise. Till this point clear? From here till here L, T1, that will rotate it clockwise. This mg is exactly at half the length of the rod, center of mass. And when this mg acts, it will rotate the rod like this. It will rotate the rod anti-clockwise. So it will be minus, because it is anti-clockwise. This distance is L by 2 and the force is mg. Next, 2 mg. It is at a distance of L by 4. 2 mg also rotates it anti-clockwise. The moment it rotates is anti-clockwise, it is minus. So minus L by 4 into 2 mg. This whole thing should be a big fat 0, because the total torque must be 0. Clear till this point, everyone? Okay, solve this. Actually, you will see many things will be cancelled also, like this L and this L, this 2 and this 4 will become 2. Okay, so what shall you get? Solve this, guys. From here, you will get T1 is equal to, bring this on the other side, mg by 2 plus mg by 2, which means T1 will be, simply put, mg. T1, are you getting it as mg? How many of you got it? How many of you got T1 is equal to mg, guys? If you got it, very good. Now put this T1 over here. Put this T1 over here as mg. Solve this for T2. How much do you think T2 will be? 3 mg minus mg, which will be 2 mg. Perfect. This is the second tension. Find the tensions. We have found both the tensions. That's how you solve these problems. Did you understand it, guys? Everybody, here this is a very good problem of equilibrium where using net torque and net force is 0, you have found the individual unknowns like the tensions here. There is another interesting question on equilibrium related to toppling. And you would have faced this if you are pushing a box, a big almirah or a big box. Sometimes it happens that this box might topple. It might basically topple. And when a box topples, it just has overcome from its equilibrium. So when it is just about to topple, the net force is 0. The net torque is also 0. The net force is 0. Net torque is 0. Anything little bit more also it will topple. So when questions come, when will it just topple? What is the condition for it to just fall over? Okay. Then it is also a problem of equilibrium, because when it is on the verge of toppling, when on the verge of toppling, it is still going to be in equilibrium. That means net force will be 0, net torque will be 0. Keep this in mind. Net force will be 0 and net torque will also be 0. Let me demonstrate an example for all of you. Imagine there is a tall object of height 2h, base h, and somebody is applying a force exactly at the midpoint. Somebody, or maybe over here, maybe on the top, somebody is applying a force over here. This is very, very rough, so that it implies that there is no slipping whatsoever. The box does not slip. Question is, in this particular thing, find minimum F to just beginning to topple. For it to just topple, what should be that minimum value of the F? Okay, ready to solve this? Ready to solve this, guys? Everybody with me? Everybody with me? All right, so let's begin. All right, so when it is just on the verge of toppling, just imagine it will rotate about this point. The diagram will almost be like this. It would have almost lost contact from all these points. About this point, it will just begin to rotate. Almost, but it is still right now at equilibrium. Since all these points have lost contact, so there can't be contact force here. So the normal force would have shifted over here. Did you understand? This is the edge about which it will topple. All these points would have lost contact. All these points would have lost contact. That's why the normal force would have shifted on towards the right side. Great. Friction will act through that point like this. This will be the static friction. The weight of the box through the center of mass, basically mg, and that force over here. Oh, these are the only forces acting on that body. Now I know net force is 0. If you want to write those equations, we can write them, but it is of not much of use. Like even if I write net force is 0, I'll just get, okay, normal force will be equal to mg force. Normal force up will be equal to mg force down. And this force towards this side will be balanced by the static friction towards this side. Nothing I'll get from this because I don't know only the value of Fs. Mu is not given, nothing is told. So I can't find anything through this. So ignore this. So let's go to torque. But about which point? I feel this point. Let's say I call this point as P. Let's say I call this point as P. How about measuring the total torque about that point? the total torque about that point will be 0, because you know the advantage of that point. You know the advantage of that point. I could have chosen any other point. The advantage of that point is normal and friction both are passing through the point. Both of them are passing through the point means what? Means what? Come on. Means what, guys? Means what? Both their torques will be 0. 0 plus 0. One by the normal and one by the static friction. They are passing through that point. Okay. What about that force? Well, that force is at this perpendicular distance. That distance perpendicular is 2h. This 2h is that perpendicular distance, and that is that force which is perpendicular to it. So the torque will be, this force will be clockwise. So I'll put it as plus, because that force will rotate the body like that, clockwise, will be 2h into F. R into F is the torque. This mg from this point, about this point, will rotate the body anti-clockwise. So minus, like this. How far is mg from this particular location? Observe carefully. How far is this? Come on, guys. Look at it carefully. Look at it carefully. How far is this point from this point? This is h. Won't this be h by 2? Won't this be h by 2? Very good. So can I say this will be minus, because this is anti-clockwise. This mg will create anti-clockwise torque. So that's why minus h by 2 into mg. Whole thing is 0. All the forces F, N, mg and Fs. N, Fs, F and mg. All forces, torques are considered. Done, done, are done. So let's see what do we get. Let's see what do we get. Bring these people on the other side. So 2hf will be hmg by 2. You can see that h cancels. Bring that 2 below. F will be mg by 4. Oh, this is that minimum force needed for it to just topple. This is the minimum force needed for it to just topple. What a question, right? All right. Oh, Ambika ma'am is texting. Okay. Don't worry, Ambika ma'am. The session is just going to be over now. All right. So, my dear students, this was anyways the last question. Let me also remind you that there is a NEET test series which is called as the amazing Super 30 test series, where you are going to get free tests. Did you hear it? Free tests from 1st November to 3rd November. All India level, thousands of students have already registered. These are mini test series, and you will feel like doing more and more. What more you want? You get complete analysis, amazing quality of questions with solutions. They are created by the best of the best educators by our team. This is absolutely free of cost. I want each and every one of you to enroll in this for absolutely free of cost. Not just that, there is another absolutely free of cost thing which I have told you before also, and that was your special class coming up for physics in this week from 4th November to 7th of November. Starting off with PYQs of mechanics, PYQs of modern physics and logic gates. The entire concept of logic gates with problems. All of this in the free special classes. Make sure that apart from the special classes, you are a part of the Avenger 3.0. The last mile is going to go on. The entire recordings will be available to you. My lectures, the entire Avenger team's lectures. I have put in my 110% in these lectures, so you don't want to miss this, because this will be a game changer for NEET 24 and NEET 25. I can guarantee you 180 out of 180 marks if you follow these lectures sincerely. Link is there in the description box. Make sure you are using the code CAPTAIN for your Captain Shreyas to get the maximum prize benefit. Right? So I would love to see you soon in the special class, in the test series and the Avenger batch. What more you want, guys? There is no way you can get less. Leave a comment after this video ends on how you learned, how you enjoyed this session, the part 1 of rotation, and say part 1 done, waiting for part 2. Part 1 done, waiting for part 2 of rotation. See you. Thank you for liking. Thank you for subscribing. Bye bye. Hasta la vista. Take care.